So with the channel blanket, it's business as usual, even with channel bonding. The channel blanket is the only technology capable of supporting 802.11n HT mode and 802.11 BG clients, all within the 2.4 GHz band. That's simply not possible with the microcell architecture due to the lack of channels. So to sum up, the microcell architecture cannot handle channel bonding on 2.4 GHz. The channel blanket can handle channel bonding on 2.4 GHz, and furthermore, the channel blanket architecture also enables the bonded channel to be pure N for maximum throughput. Legacy clients can use the other 2.4 GHz channel blanket and will still get good service. The result of all of this is that for 802.11n HT operation, the microcell players have been forced to abandon the 2.4 GHz band and focus on the 5 GHz band. So now let's take a look at whether channel bonding is more viable in the 5 GHz band. The first step is to take a look at the 5 GHz wireless LAN spectrum. The 5 GHz band is actually split into 4 subbands: UNII1, UNII2, UNII2 extended, and UNII3. By the way, UNII stands for the Unlicensed National Information Infrastructure. As you can see, there is much more spectrum at 5 GHz to the extent that 11 40 MHz wide channels are supported in theory. But the question is reality as good as it looks here? The answer is no. There are two entities that lower the actual bandwidth that is available at 5 GHz. One is DFS and the other is spectrum noise. DFS refers to dynamic frequency selection, which is the process that an AP must follow when it encounters radar signals. This can happen on the UNII2 and UNII2 extended subbands, which contain the majority of the 5 GHz channels. Now what this chart shows are the number of 40 MHz channels available in each subband, and the total number of channels across all subbands is listed at the bottom of each column. As the chart illustrates, there are 11 channels available when channel bonding is used. That's still not enough to avoid some co-channel interference in medium to large wireless LAN installations, because the channels will need to be repeated. 5 GHz cells are somewhat smaller than 2.4 GHz cells, so you can run out of unique channels relatively quickly. Also, even the total of 11 channels depends on using DFS spectrum. On a DFS channel, if any interference is detected, the channel is blocked from wireless LAN use for a minimum of 30 minutes. And to compensate for the loss of the DFS channel or channels, the wireless LAN controller needs to perform an automatic channel reconfigure causing clients to be knocked off the air. If we want to avoid using DFS channels, it's important to note that there are only 4 40 MHz non-DFS channels in the 5 GHz spectrum. So the answer is that while the 5 GHz band is significantly better for channel bonding than the 2.4 GHz spectrum, it still has its limitations. So to sum up the discussion of 5 GHz and DFS, if DFS is leveraged, there are 11 40 MHz channels. If DFS is not an option, only 4 40 MHz channels are available. Now we have to discuss the other channel consumer, spectrum noise. As you can see in this chart, there are a number of services that use the 5 GHz spectrum, and that number is growing. So while the 5 GHz spectrum is in general less impacted by noise than the 2.4 GHz band, the 5 GHz band is also prone to some noise from other wireless technologies such as WiMAX and ultra-wideband. There are also other interference sources in the 5 GHz band, such as transportation radar, weather radar, cordless phones, and security sensors. It is also important to point out that the 5 GHz band is relatively wide, ranging from 5.170 to 5.825 GHz, and there is likely to be interference somewhere in the band. One is unlikely to have 11 noise-free channels. So the realistic number of 40 MHz 802.11n channels at 5 GHz is as follows. 4 channels are possible if the DFS channels are not used. If the DFS channels are used, then 6 to 8 channels can be reasonably expected after factoring in spectrum noise. The implication for the microcell architecture is that 5 GHz is the only option for full-speed 802.11n operation. There are enough 40 MHz channels for cell planning. However, there are not enough channels to avoid channel repetition in medium to large enterprise settings. So co-channel interference will still be a major problem in this context for the microcell architecture. The implication of the 5 GHz spectrum for the channel blanket architecture is entirely positive. 5 GHz increases capacity even further. When using channel bonding, 4 channel blankets are now possible instead of 2 at 2.4 GHz. 2 blankets are run at 5 GHz and 2 channel blankets are run at 2.4 GHz when channel bonding is in use. It's very important to point out that the channel blanket is also a DFS-free solution. UNII-1 and UNII-3 provide enough channels for the channel blanket architecture. There is no dependence on the DFS channels. Next, in part 2 of this video, we'll take a look at why co-channel interference is still a problem for the microcell architecture at 5 GHz, and we'll discuss the rest of the topics on our agenda for the challenges of 802.11n.